A short introduction of me. I am Paolo Mainardi. I come from Italy, Milano. I am the CTO and founder of Spark Fabric. We are a small company based in Milan. We are 25 engineers right now. We are growing, we are hiring. If you're interested to know more about us, you can check out our website and my website as well. And yes, what is the topic of this talk? Today we are cover some aspects. I will start by explaining you what is the hype cycle. You know that we are very affected by the hype cycle, especially in our sector. And according, we will see what is the hype cycle according to Gartner and why it's important to know it. I think that it's very important because as we are very affected by the hype cycles, when we pick up a technology from the bookshelf, we are basically doing a decision that will come along with us for years. So using these techniques, we can better choose the technology for our new startup or for our current business. Then I will review some basic serverless concepts, talking about functions, backends, and container as a service, and so on. To finish, I will try to mix what is serverless and what is Kubernetes and how to make them work seamlessly. And you know maybe that Kubernetes it's very strongly binded with infrastructure where it runs, and the concept of servers. So we will see how to implement the serverless paradigms on something like that. As you can see here, the hype cycle, it's a branded graphical representation developed by American research information technology firm Gartner. Maybe you already heard about them for their famous reports, which is the magic quadrants of cloud providers. And is here to represent the maturity, the adoption, and the social application of emerging technologies through 5 main phases. We know that humans are famously better predicting the future of technologies, and we tend usually to overestimate technologies' abilities in the near term and massively underestimate in what they can do in the long term. So, for example, if you could ever talk to myself of 3 years ago, I would probably bet everything on blockchain or 3D printing. Strongly convinced that we were very close to a new technology breakthrough that was changing everything, but you know, then the things slowed down, almost faded from the mass uses. But we can apply the same thing for the old technologies. AI, 3D printings, they are waves. So actually, we can use this tool to better understand the market and, according to our confidence with the risk, choose or not to invest or pick up that technology or product. So the very first phase is the technology trigger. Technology trigger is, in this stage, a potential disruptive technology is conceptualized. Also, if it's just a proof of concept and nothing is yet proven. I don't know what happened. You know what is the agenda, and we were talking about which are the phases of the hype cycle. As I said, the first, as you can see, the first stage of the hype cycle, according to the Gartner representation, is the technology trigger. In this stage, a potential disruptive technology is conceptualized. Also, if it's just a proof of concept and nothing is yet proven. For example, if we use Docker as an example, it was the 2013 when Docker was presented by Solomon Hykes. At the time, it was the CEO of .cloud. Docker company, it wasn't yet created. And with a lightning talk of just 5 minutes titled "The Future of Linux Containers," he basically changed everything. At the time, Docker was much more than a CLI tool to run Linux containers, a very nice wrapper around LXC, which are the Linux primitives to spin up containers. It wasn't even there the Docker file to create the new Docker images, so you can do just few stuff with it. But it's exploded. You know what happened next? In just 5 minutes, the talk basically changed everything. Now, when this happens, a lot of interest gets generated around the technology, then thanks to social media, contents, news, conferences, we face the peak of inflated expectations. In this stage, we are over the early adoption. The early publicity produced a number of success stories, but also a lot of failure ones. Using the Docker analogy again, the first releases of Docker was clearly ready to run production workloads, but a lot of users did it, and this generated big waves of negative press of failure stories, causing stress and disillusionment around containers, around Docker, saying that the product it was ready. But even though they always clearly state on that side that Docker was not yet a stable product. This negative press lead us to the trough of disillusionment. In this stage, the curve of hype cycle begins to descend until there comes a point when the media and press totally abandon the topic and the technology and the interest start to go off. This happens in most of the cases where the technology doesn't fulfill the hype or looks like it's not really capable to solve what promised at the beginning. Some producers are unsuccessful and fails, others start to drop the products. And this is also the phase where investments continues just for the surviving company that are still capable to improve their products, to improve the technology, to satisfy the early adopters. Then we face, if we can survive, we face a slope of enlightenment. In this stage, more instances of how the technology can really benefit the enterprises start to crystallize on the market and become more widely understood. Let's think about containers. We know now that we can really scale our applications, our workload, thanks to the use of containers. This is also the phase where second, the third generation of products start to appear from the technology providers. Let's use again the Docker analogy. Here, we can think to the product iteration of Docker Swarm that was their solution for orchestrating containers in cloud, where the last generations, they failed, but the last generation added the native support to Kubernetes, making it a first-class product to orchestrate containers in cloud again, and help them to survive after a very profound crisis of the company. Then there is the last phase, which is the plateau of productivity. Now, the last stage, in this stage, the technology is widely implemented and mainstream adopted. Its place in the market, it's very well understood, and the standards and the criteria gets defined for evaluating technology providers with the certifications and so on. So we are in a phase where the technology is stabilized, like we can say Kubernetes is now basically. But according to the Gartner Hype Cycle Emerging Technologies tool, where was placed serverless in this hype cycle? The last report where serverless was placed by Gartner in the emerging technologies was the 2017, where was placed between the technology trigger and the peak of inflated expectation. To me, it's totally correct, because at the time there was very few services. There was maybe just AWS Lambda that became GA in 2015, and all the other vendors was creating products around function as a service, a serverless product, but it was in an alpha or beta stage. Today, we are instead facing a more mature and well-established market. We probably reached the slope of enlightenment. There are a lot of serverless products, the investments are growing, and the adoption of serverless technology is becoming widely more and more accepted also for enterprise workloads. According to Gartner, today, in the next 3 years, serverless will become the predominant cloud computing model, considering that really today according to the Gartner data, more than 10% of cloud workloads are serverless based. So, what is serverless? Serverless is something that a lot of people jokes about because you know, when we think about workloads, code, functions that must be executed somewhere, we need servers. Yeah, but if we compare it to another name that it looks like very normal to us, for example, wireless. We know that wires are still needed to connect our router to the network, but we as a users, we don't need to attach network cable to the phone or to our laptop. We can just consume the network and make profit of it. This is the very same concept. We can develop our code, our applications from the simplest one to the hardest, to the complex one. And we can just ship it on the cloud without worrying about how many CPU, how many RAM, how many disks I need, and which is the best networking stack I have to choose, how will I monitor my infrastructure, how will scale. This is the basic concept of serverless. So as a developer, I don't want to care anymore about provisioning, maintaining, planning. I want just to focus on my code and shipping quick as possible to the cloud. So this is the CNCF standard definition of what is serverless. It's serverless computing refers to the concept of building and running applications that do not require server management. As simple as that. So as Kelsey Tower said one time, when we have a great idea, the last thing we want to do is stop the infrastructure to run it. This is quite huge because building software, it's an act of creativity and should be sustained in all the ways possible. And also everything that can help me to reduce the time to market is helping my business and help me to just focus on the business value I'm proposing to my users, and it's pure gold at the end. So serverless, it's all about the developer experience because it offers me some unique features like it's cost and resource efficient. It allows me to scale down to zero when I don't have any load to my workloads. I can use a model which is the pay-as-you-go. If I'm using a lot of services, if I have a lot of loads, a lot of traffic to my new super application, I will pay just for the time in seconds that I will consume of that service. I don't want to pay, I will not to pay anymore for idle service doing nothing. Then it's capable to support the automation and supporting my full dev cycle from my development environment to the build environment to the CI to the prod, and it's capable to automate all the aspects that are around an application deployed on the cloud, like make it scale it, how to handling the failures and how to recovery on from that. So when we think about serverless, basically we think to the function as a service. Maybe you already know this this term, which is sold a lot from the cloud vendors. Maybe you know AWS Lambda, which is basically functions and events. Functions that are a piece of code usually written in JavaScript, but we will see later that you can develop in several languages to perform a specific task. Then there are events, which is a response to something that happens in the cloud, like, for example, an HTTP call or a file loaded in a bucket or a new entry stored in a database that triggers the functions to do something. So let's see some very simple use cases. Like they are just a bit more advanced than the Hello World, just to make you understand what is, which are the use cases, simple standard use cases of serverless, of function as a service in this case. Let's imagine that we have to translate files from Italian to Spanish,
And our non-functional requirement from our clients is that we have to scale up on demand, because maybe they have tons of files just in a fixed hour in the morning, maybe from 10 to 11. And they want to just pay for the service. They don't want to build an infrastructure and paying when no files are translated or uploaded to the service. So the infrastructure we build is this one. It's very simple. We have a client that could be an API or a human uploading a file on a cloud storage, which is something like an hard drive, cloud hard drive, where I can upload files. This file, this cloud storage, as is a serverless product of the cloud vendor, it is capable to generate an event saying that, hey, one file has been uploaded here. And we can attach to this event, and we can trigger our function. Yeah, we trigger the cloud pub sub service in this case, where the files gets stored on the pub sub messaging to make it capable to run multiple functions. And then this service, which is another serverless service, is triggering the function which basically use the cloud vendor service to translate the file and upload back in another folder the translated file. So what we have at the end of the day is an infrastructure capable to translate files, tons of that, without worrying about to pay something when we don't want to translate nothing, basically. Another use case where we want to process real-time data and push notification to the mobile client. So we have two things to do. We have to process the data and push some notifications. And also here we want to scale up on demand, and we want just to pay what we use. Let's imagine that we are bidding something for the stock market. We know that the trading hours are between 9 and 6 p.m. And between this time frame, we receive a lot of raw data. So as you can see, there are clients that are pushing the raw data to our pub sub ingestion queue, which trigger the function which basically implement our business value of our product, translating the stock raw data in something more useful for our users. Maybe we are monitoring some indices. And then we push it back, the converted data in another queue, which trigger another function, which are our the second our business value, which take this data and push the notification to our clients. When the trading hours are over, we basically we are not paying nothing, because we are not receiving nothing from the stock market. So, which are the key properties of function as a service? Function as a service are much like standard functions you are used to write in conventional programming languages. They are small, they are separate units of logic. They take an input arguments, process them in some manner, and then return the result. So they are stateless, which means that you are not in control of, as you are not in control of the underlying server infrastructure, you can save, for example, a file to disk, or and expect it that at the next run you will find the file there, and because any invocation of the function could potentially be executed in another server under the hood. Ephemeral, because they are designed to spin up very quickly, do their work, and then shut down again. They are designed to have a maximum execution time according to the vendor imposed limits, which is usually seconds or just a bunch of minutes. So if you are processing a big data, for example, where you need to run a job for hours, serverless functions are not the best scenario to implement it. They are event triggered because as we saw in the previous slide, we can trigger the function based on some events, which could be HTTP call, which is an event made by a client, by a user, or another event generated by another cloud service like a PubSub or a database and so on. And they are scalable from 0 to n, and they have a problem, which is the cold start, because as they can scale to 0, it means that they are not deployed basically nowhere inside the cloud. So when we start from scratch a new function, we are facing a phenomenon called cold start, which is, broadly speaking, the time the cloud vendor spent to allocate the function, the resources to spin up the function on a machine and make it available to the caller. You can imagine the time you spent when you must run a new Docker container, when you must pull it, and then you must run it. This is basically roughly the time the vendors have to spend to run the functions. But you pay this cold start just for the first time, because at the next invocations, the function is kept warm. And we are talking about from a bunch of milliseconds, 100 milliseconds, to 3, 5, 10 seconds, depending on also the language runtime are you using, and if some other characteristics. Like if you are running the function inside the VPC on AWS, the time is like 10, 15 seconds, but they are working on to fix it. Another property that it's fully managed by a third party, like AWS Lambda, as I said, Azure Function, Auth0 Web Tasks, Google Cloud Function, and so on. But serverless, it's not just function as a service. We have a plethora of services which are the glue between our functions, which basically handle the data, and the services that store the data, for example. As you can see, if we cross the serverless ecosystem and the platform as a service ecosystem, you can imagine, for example, GKE from Google or Heroku. They have always something to store the data. That could be like a NoSQL database, like Google Firebase, where basically you have something that responds to you like serverless, because you are not paying for Firebase on other services like that. How many CPU, how many gigabytes, or how many instances of that database are spinned up for you. But we are just paying the bandwidth that we are consuming when you are consuming it, and the time, the service, for example, the number of queries. But we can apply the same concept also for to the other services like PubSub, BigQuery, and so on. So serverless, it's also about the billing model. We can consume some traditional service like a relational database like MySQL, but using it like serverless, using a serverless paradigms at the end, because we are just paying what we use. One nice definition is this one, where a serverless solution is one that costs you nothing to run if nobody is using it, excluding the data storage, which is the persistent part that you have to pay it all the time, of course, because someone must keep the data for you. You are consuming space. So to recap, what is serverless? Serverless is something that requires no servers. It's idiomatic, that allows me to use the power of my tools without any kind of modifications. For example, I don't want to be forced to use a particular PHP libraries or a particular Node.js runtime. I want to exploit all the power of my tools. And it's event-driven. I can. It's capable to generate events from all the services involved in order to make the architecture respond to some events. And it's free of lock-in, so I can write a function that is capable to run on AWS Lambda, and I want to take it as is and deploy it in another server like Google Cloud Function, or spin up that function on my laptop. This is in an ideal world what is serverless. But today on public cloud, the situation is a bit different, because we have a limited runtime language support. We can, for example, deploy a Ruby function on the public cloud function as a service. And the vendor usually proposes a proprietary mechanism to package and deploy the function. And then there is the lock-in, because the event format between the services it's proprietary, and the run times where I run the functions is some way locked in. Because, for example, if I want to add a new extension to a PHP function as a service runtime, I cannot do it. Yeah, that's it. It's not really the case, because with AWS or other services, you have some mechanism to add some custom libraries to the runtimes, but yeah, they are not officially supported. So let's see what is the lock-in. Starting using an example, we implemented super complex applications. You can see that is capable to convert CSV file to JSON. We implemented for GCP. So we are capable to receive these CSV files from pub sub queue, and using a functions to convert it and give them this JSON to our user. Then our marketing team comes to us, then say, okay, we sold this solution to another user, but they are not using GCP, they are using AWS. Perfect. We can select the same services on AWS. Instead of cloud storage, we use S3. Instead of PubSub, we use SQS. They are the very same service. And we reuse the cloud functions we implemented the Google Cloud Functions. So we run the code, everything is broken. Why? Because as you can see here on the left and the right side, this is the event we receive from the two vendors. The left one is from AWS, the right one is from Google Cloud. They are totally proprietary. So to solve this, we have to implement something like event processor capable to take all the proprietary event formats and convert in something standard. We must define our standard to process the function. So we have to implement a new layer of our application, and we have to extend our initial cloud function to support it. But we don't have to invest a lot of time creating a new standard, because a standard exists, which is cloud events. Using cloud events, we can just rely on a standard format and make our function working seamless. But the problem is that today cloud events is not very implemented in the public vendors. But the cloud events, it's a specification. It's just a specification for describing event data in a common way. It's a project created by the CNCF. It's a joint collaboration between the big vendors like AWS, Google, IBM, Alibaba, Microsoft, but they just contributed to the standard. Right now, maybe they will adopt the format on their services. Right now, it's just supported by Azure with the Dev and Grid, which is a service capable to receive Azure events and push it back like cloud events standard in a standard format, basically. Well, so the question is, why serverless on Kubernetes? Because we want to, as developers or as operators, we want to rely on the same very cool features of developing application using serverless, but using also the extensibility and the power of Kubernetes and containers. Let's see what is the developer experience on Kubernetes today. We start to write the code, we finish to write it, and we want to push it in the cloud. So we write the code, we build the Docker image, we push the Docker image to a registry. We are forced to do it. We must write tons of YAML manifest to deploy it. And then we must apply it, hoping that everything will be fine, basically. As you can see, any step we add to the writing code and shipping it, it's a waste of time, basically. What we want to do is just write code and ship it to the cloud as developers. So, developing on Kubernetes is not easy. It's not the right abstractions for end developers, because we have to know a lot of APIs. We must know what is a deployment, what is a service, and we are dealing with networks. We must know what is an ingress, what is an HPA. We have to choose the monitoring solution. We must secure the communications between the services. There are a lot of moving parts laying around between our code and the infrastructure. So, but for everything I said now, it's a great platform to build a platform as a service on top of it because of that primitives and its extensibility. So let's imagine that we want to build a serverless experience on Kubernetes. So let's see which are the parts we will need to implement it if we want to by ourselves. We need something to wake up workloads on a request, like it works like the functions, basically. We don't want something that is running all the time somewhere. We want to trigger an event and create the service just when we need it. Then we need something to scale up and scale back to zero our workloads, like the functions. And something also to turn our code into a container to skip all the boring parts of writing the Docker file, building it, pushing it in our register, and so on. And an eventing system capable to have configurable sources and subscriber, which will be our functions. But we don't need to implement by ourselves all these kind of things, because it will require millions of dollars, maybe, and a team of 50 engineers. We can just rely on Knative. Knative is a Kubernetes-based platform to build, deploy, and manage modern serverless workloads based on containers. And it offers features like scale to zero, auto-scaling, and an eventing framework. It's a project born in Google, and they release it as open source like they did for Kubernetes. And it attracted a lot of interest between the community and also from the big companies like Pivotal, SAP, Red Hat, IBM. They are creating products based on Knative, or they already created a product based on it. So let's see which are the Knative building blocks. We start from the platform. The platform is based on Kubernetes, and it's all primitives plus a service mesh. Service mesh, it's a teeny layer between our services. It's a network-defined software layer that allows us to do things like upgrading the connection from raw to secure using MLTS automatically. We don't have to implement it. We can define advanced traffic routing between the services and so on. What it happens inside Kubernetes, it's a proxy. Mainly, it's like a sidecar proxy between our services. And then, on top of it, we have the three big primitives of Knative, which are also three projects, which are build, serving, and eventing. Let's see in detail what they are. Knative serving, basically, it's one of the main components. It allows us to do a lot of nice things like scale up and scale back to zero. This is something that Kubernetes doesn't support natively, like the concept of scaling to zero. When you spin up a new deployment, you must have always at least one instance of the application you are running. So it's extending the behavior of Kubernetes, allowing it to scale up to zero, to scale down to zero. Sorry. Then, thanks to the service mesh, we have a fine-grained traffic routing. We have automatic metrics and telemetry between our services. Also, also in this case, thanks to the service mesh. And we have a point-in-time snapshot of code and configuration, creating a sort of service revisions. This is quite nice because we can deploy, for example, multiple concurrent services, and we route the traffic between 80% to the old one and 20 to the new one. If everything is fine, we can switch all the traffic to the new one. We can inspect a lot in how the traffic, the load is coming inside the services, and decide how to route the requests based not just on the number of revisions we have, but also, for example, by expecting the headers in the request. Let's see how we define a new application inside Knative. As you can see, we are just, maybe if you are familiar with Kubernetes, everything is must be done in YAML. That's why a lot of people jokes about when you work a lot with Kubernetes, you became a YAML engineer. But here we are basically with 15 YAML lines. We are defining a full application stack, basically replacing a deployment, the service, the ingress. We are just saying that we want to run a new service, which is not a Kubernetes service, as you can see, because we are relying on the API from Knative. We are defining an application, which is called a service, and we specify the containers. We can inject some environment variables, and so on. We can also go deep in the details, like extending, extracting Knative to do something like, okay, I don't want to be affected by the cold start, so I can say to Knative, okay, for this service, I want to have always at least one instance of it. And we can also changing the aspect of how the service will scale. For example, in this case, we are saying that to Knative that we want to scale based on the concurrent request. Maybe if you are familiar with the Kubernetes, you know when you do these kind of things, you are referring, I want to scale based on how many CPUs is consumed, or how many RAM is allocated by the processes. So here we are in a more abstract scenario, because we are just saying to Knative that we want to scale based on the request, like a function, basically. The second big component is Knative Eventing, which is a complete eventing system for event-driven apps. It has two components, which is the broker, which is the main components capable to act to receive all the events coming from more disparate sources, and the trigger, which is the glue between our service and the events that is coming in. This is how we define trigger. Basically, we are just saying that for a message coming in, as you can see in the filter part, the message who has these two attributes, the type and type and source, we want to subscribe it, we want to send it basically to our service called Hello World Go. We are just instructing the broker to filter the message using that pattern and send it back to the service we are defined that. We can just, as you can see, basically it's just HTTP message to the broker with some cloud events header, standard headers, and the message, the content of the message that we want to send to the service. We can also, of course, we will use in a real production, real business scenario, someone that will generate the message in an automatic way, but as you can see, for the sake of simplicity, that is the message that is coming to the broker, that will come to the broker and coming to you, to your service. So the third component is Knative Bid, but there is a problem because it has been deprecated some releases ago, because they say that bidding the image, the source to image, it's a so big, broader topic that it requires a new its space and a new project. And they choose to close it, and the community took it, the project, and created another project which is called Tecton Pipelines. Tecton Pipelines, basically, it's born from the Knative Bid component. They rebranded it, they created a new community around it, and they extended it, of course. This project, it's not only there to provide something to build the Docker image in a simpler way, but it aims to provide something to declare CI/CD pipelines using the Kubernetes style definition. Then another nice aspect that the build can run completely within Kubernetes using projects like Canico and BuildKit, so we don't strictly forced to use the Docker daemon, which has some security problems because you need a daemon. It needs to have the root access and so on. And as it is a very big project, as I said, it's openly governed. They created a foundation which governed the project, which is a branch of the CNCF. So what we can do with Knative? We can, as a developer, we can use it to deploy our stuff in a more streamlined way than the raw Kubernetes. As an operator, I can put a level of abstractions between Kubernetes and the devs. And also I have for free the fact that I can keep the costs under control because the workloads can scale to 0. So I will consume less power, I will consume less virtual machines and so on. I will this for free basically. And as a platform architect, I can decide that I want to build the next great platform as a service based on containers using the already implemented Knative components because they are modular. So let's see some Knative native platforms that are available today. One of the most advanced one to me, it's the Pivotal. It's the one from Pivotal. It's called Reef. It's an open source project from Pivotal, but now they are acquired from VMware. It has a deep Kubernetes integration using CRD, so it's using native APIs. It's pluggable. It's pluggable, so now you can choose between Knative or Core. You are not forced to use Knative, but you as a user behave as an end user always like serverless platform basically, and they pick from Knative just the serving part because they decide to build. To implement something from scratch to build to create the containers, and they are totally based on the build packs, which is another CNCF standard. Maybe if you know Heroku, you know what are the build packs, but basically, broadly speaking, it's something more higher level of from Docker files, and they are capable to understand based on the framework, on the language you are using, which are the best things to do to create a container without asking you to provide the Docker file. And another good point that they have a CLI tool to manage the entire life cycle. This is gold because when we are developing, we need a lot of small things, and if we can do it using a streamlined command line, it's super cool. Then there is another project, of course, which is backed by Google. Knative, it's a project born from them. It's fully managed by Google Cloud Platform. It exists in 2 versions, which is the Cloud Run service and the Cloud Run on GKE. Basically, the difference is that with Cloud Run, you have just the gcloud command line to manage your containers as functions. And you know that underlying Knative is working. If you expect the YAML generated, you can see it, but you cannot interact or change the Knative behaviors. You take it what the service offers, basically. But if you want to go more advanced, then you also you have a GKE cluster. You can decide to ask to GCP to install Google Cloud Run on your cluster, and basically what you have at the end of the day, you have a Knative plus Istio installed and managed by Google into your cluster. Then there is OpenShift Serverless, which is a full stack Knative product. It's not yet stable. It's a technology preview. It's in a technology preview feature only, not yet supported. And it's as I said, it's based on the full stack of Knative serving plus everything plus Tecton pipelines. And yeah, there is a breaking news. The breaking news, which is that Google decided to that they will not donate Knative to the CNCF Foundation. and they try to explain why, but the reaction of the community, it was very harsh. As you can see here, Brendan Barnes and Joe Beda, that are the two of the co-founders of Kubernetes. We should remember that the CNCF and all the cloud native ecosystem has been created with that spark when Kubernetes was donated to the Linux Foundation. I think 6 years ago. They decided to create this big community of developers and operators, promoting the open governance and creating what we today call Knative. So maybe this will affect the adoption of Knative. Maybe Google will change the idea, but we'll see. Right now, Knative it's an open source project. You can contribute to the project, of course, but it's not under the CNCF umbrella. There are a lot of other solutions more simpler than Knative, like that just use the Kubernetes primitives to implement something like a serverless platform. I try to collect most of them here. The most implemented one, as they basically have a common set of features. Most of the projects are older than Kubernetes, like OpenFast, which is a project by Alex Ellis, which I guess, if I'm not wrong, was created at the time of Docker Swarm, then integrated Kubernetes. It's a very nice project. There is also Kubeless, which is a project by Bitnami and so on. They have they are much lighter than Knative if you install it on your cluster. They support containers, of course, because we are running them on top of Kubernetes. All of them have a custom CLI to support the entire life cycle. They are written in Go, so they are. If you are familiar with Go, you can easily extend it. We know that Docker and Kubernetes are based on that, so it's quite easy to glue this service with Kubernetes, with the Kubernetes API, for example. And they are backed by big vendors, Oracle, VMware, so they are not there to disappear very soon. If you want to have a better idea of what is serverless for now, the CNCF created something like the serverless landscape. Maybe you already saw the CNCF Cloud Native Landscape, which is a group of cloud native projects. And as the serverless ones, was very big, they decided to keep it out from the standard landscape, and they created this one, where they basically grouping the services based on if they are platforms, frameworks, and etc. So serverless on Kubernetes allows us to have flexible language runtimes based on containers, which is a plus, because if you are developing our application using the most desperate language, with the standard function as a service, we can not do it, because we are forced to use just a set of languages supported. But here we are using containers, so we can just ship it what we want, basically. We can run it on multi and hybrid cloud and on my laptop. This is one of the features that the standard function as a service don't allow it. And we can mix and match stateless and stateful workloads, always thanks to Kubernetes. And but it means to have a lot of new moving parts running on our cluster. For example, when we install Knative on our cluster, we are going to install 100 plus CRDs, a lot of components. Maybe using the other services, the situation it's very different, because they are very lighter. And yeah, it's another set of components you have to manage, but you have great benefits using it to develop your new new generation of workloads. So in the cloud platform, I think that in the next few months, here's the Kubernetes paradigms and the serverless ones will converge, and will be much easier to using Kubernetes to as the new operating system platform to build our next generation of applications, and maybe we will say to Kubernetes to just run the code instead of running the containers and so on. Muchas gracias.